I am going to outline some ideas from synthetic projective geometry, the study of incidences of lines and points, and then relate them to graphic statics. It is particularly important to take account of the duality between lines and points. 4 points A, B, C, D may determine a quadrilateral, while corresponding lines in another figure, A, B, C, D, may determine a quadrangle. There is complete correspondence between the two figures. The line connecting points A and B in the quadrilateral corresponds to the point of intersection of lines A and B in the quadrangle. Diagonals of the quadrilateral, AC and BD, correspond to intermediate points AC and BD in the quadrangle. A quadrangle and a quadrilateral are connected by a projective transformation called a correlation, which transforms points ABCD to lines ABCD. A projective collineation transforms one quadrangle or one quadrilateral to another. A particular type of collineation is a homology, where a point and its image are on the same line radiating from the center of the homology, and the line and its image intersect on a line called the axis of the homology. This can be more neatly expressed as points and their images are perspective with a point, and lines and their images are perspective with a line. Finally, there is a correlation that sends a quadrangle, in this case A', B', C', D', back to a quadrilateral ABCD. The relation between synthetic projective geometry and graphic statics was summarized by CULMANN, at least for systems of concurrent forces. In his diagram, we have forces 1 through 5 along with pole O sub K that transform to the intersections of funicular lines representing a set of forces with point of concurrence O sub S. I would like to make CULMANN's notions a little clearer by referring to the characteristics of projective geometry that opened this talk. Given a system of 4 forces A, B, B, C, C, D, and dA, and a pole, P, it is possible to induce a correlation with the funicular polygon, lines A, B, C, D, with a point of concurrence of the forces at O. This automatically locates the diagonal forces AC and BD, or any other related forces on the funicular diagram. The funicular diagram, which represents the lines of action of a set of forces in equilibrium with AB, BC, CD, and DA, can be transformed by a homology with center O to any other funicular diagram without returning to the force diagram. The transformed funicular polygon corresponds by correlation to a force polygon with a new pole, P'. Similarly, a shift in the point of concurrence in the funicular diagram can induce a homology in the force diagram that results in a different group of forces in equilibrium, but the same funicular polygon. This table summarizes all of the different force polygons and funicular polygons that we've looked at and the transformations from one to the other. The first thing that we showed, for instance, is the part that's on top where you have a force polygon A, B, C, D that you transform to a funicular polygon A, B, C, D. That funicular polygon can be transformed by homology to a different funicular polygon and the same point of concurrence. And given an unsymmetrically loaded arch, such as the one shown, it is possible to choose an arbitrary pole to construct a funicular polygon, ABCD, as a complete quadrangle with all of its points of intersection. Any 3 points in the arch can then be chosen in relation to the shape of the arch in this case points A, B, B, C, and C, D. Given the homology between funicular polygons, the new polygon can be constructed by incidences. Lines B and C are determined by these 3 points, and all of the rest of the intersections are also determined by the properties of the homology. This results in a funicular polygon corresponding to the shape of the arch. This construction works equally well going the other way around, that is to say, finding new loads in equilibrium for a different point of concurrence. Based on the previous example, we've located a new point of concurrence. Instead of an ideal point, we've located this point P1, and all of the loads will converge to that point, and we can assure equilibrium by simply practicing a homology on the force diagram. And the result of that is that we will also have the directions of these new loads in equilibrium. In conclusion, we can basically say that we have not been able to get to the point where we can talk about some of the anomalies in this construction and how to resolve them. I will have to refer you, at least for a starting point, to the written paper, but the issues that are really important here are trying to deal with parallel forces. They create a little bit of a problem in the strict construction of projective geometry transformations applied to graphic statics. And then we haven't even started to talk about non-concurrent forces, which are a significant area for us to work in and a significant issue for the application of some of these ideas. Thank you very much for your attention.